Hi, so the purpose of this video is to show how you can use Stardist to detect brown stained nuclei in DAB stained images without having to train a model yourself. So just to give you some context, I hope my screen is recording. I got a few messages actually with regards to comments about the Universal Stardist for QuPath script and its capacity to detect really kind of intensely brown stained nuclei. Now, in the current version of this script, what ends up happening for the HDAB case is it will extract the hematoxylin channel, normalize it, and pass that on to a one-channel trained model, such as DSP 2018, which is trained on immunofluorescent stained nuclei, or sorry, DAPI stained nuclei. This is fine, except if you have really intense DAB staining. Because really intense DAB staining can basically mask hematoxylin and brown and vice versa. So it basically leads to a lot of challenges stemming from the fact that deconvolution typically fails where you have in cases where you have very high optical density. So on that note, I decided to show a quick video on how someone such as myself or an advanced QuPath user would go about adapting some of the standard Stardist code, um, code that's available in the QuPath documentation, and how you can adapt this to perform brown stained cell detection in cases where the current universal Stardist for QuPath doesn't work out as well. So, on that note, let's begin. First things first, I will be showing this demonstration on two images. This is one case stained for a marker of hypoxia with intermediate brown staining. We have some cells which have no depth whatsoever, and then the more intense cells have intermediate levels. No saturation of optical density limits. So first things first, we gotta specify color vectors. Uh, Personally, I opt for a more automated approach to do this, so you can zoom in, find a region that contains, brown areas, not brown areas, and a little bit of slide background. Let's go with this area. You want to have, your white space be reasonable so it gets detected as the modal value. And after drawing the rectangle, you can go to preprocess and estimate stain vectors. All you have to do is click auto, and depending on the size of the area and how computationally powerful your computer is, this can take anywhere from a couple of seconds to a few minutes. I wouldn't recommend running this on a full slide image because it could take quite some time. Anyways, as you can see, color vectors haven't really changed that drastically from the default values, but nonetheless we'll still use them. And as you will note, these custom color vectors now show up in the workflow tab, so we could potentially use this for other images. Now, if we zoom in, we can start swapping between the hematoxylin channel, the DAB channel, and residual, but we don't really need to use that for anything. First off, what we're going to attempt to do is perform DAB detection using our Universal Stardist for QuPath script, and then we will work on having a custom built solution for cases where we have really intense DAB staining. So on that note, let me just quickly load up my script. I'll use the GPU accelerated version, but it really won't make that big of a difference. And I'll just shrink down the area just a little bit because I don't really have, interest in waiting for this whole thing to finish processing. All right, so on that note, let's just make sure any parameters we need to set are set. Because we're working on a bright field image and this script is nothing more than an agglomeration of multiple case statements or else if statements, we will set param channel to 0 because the first channel of the deconvolution is going to be the hematoxylin in most cases. Other than that, let's give it a shot. So, detection bright field image using single channel trained model. Oh, this is completely my fault. The first channel, I should read my own documentation. The first channel in an image is channel 1, therefore channel 0 doesn't exist. Off by 1 errors. Okay. So if all goes well, hopefully we should get reasonable cell detection. And I'll only turn on the nuclei, because truthfully, when you run Stardist, you're only detecting nuclei, not the whole cells, assuming you're using one of their pre-trained models. Yeah, doesn't seem to be, that bad. Well, let's give it a more challenging case. So, presumably one of the reasons why this guy messaged me is because he's attempted to use the script and it didn't give satisfactory results. In this case, I'm not getting good detection using models. If I use either bright field, use either of the single channel models, it sort of detects HDAB with larger nuclear borders. Yeah. So on that note, let's find a case with more intense dab staining. I believe this sample should suffice. Got the color vectors. This will just let me replicate the full color vector adjustment. Also, before I forget, I will turn on input display so you guys can actually see what buttons I'm pressing. I believe this is the sample. Yeah, so in this case, we actually have relatively little hypoxia, but the hypoxia that we do have is fairly severe, and it manifests as more intense brown staining. Also, another thing to note is all of these images in this dataset were actually stained, scanned, and imaged in batch, but just looking at the thumbnails, you can see that there's quite a lot of variability. If you want to set color vectors for an entire project, what I recommend doing is creating a training image with one representative subset from each of these images, automatically detecting color vectors and applying them to all images in your dataset, but that's a topic for another time. So let us start. Let's first run this, because I don't remember if I ran it, and run Universal Stardist QuPath. Let's take a look at what we get. So, despite the fact that we very clearly, well, not very clearly, but despite the fact that we do have nuclei here that are intensely brown staining, this model is not picking it up. The reason being is that Universal Stardist for QuPath, when it deals with a bright field image, it will deconvolute the image and extract the hematoxylin channel and use that for detection, which is fine in most cases unless you have really intense dab staining. Now, it's easy for me to say that, oh, next time, crank down the use of the secondary antibody, have less or a lower concentration of diaminobenzene, benzene or whatever. But instead of complaining, about the images and they've already been acquired, there's nothing much we can actually do about that. Let's try and find some solution or creative workaround. Now, the first creative workaround is simply changing the channel to channel 2, and that should be the brown stain channel. But what's going to happen is you now start missing the hematoxylin nuclei, or hematoxylin positive nuclei. Now, at this point, you could technically run the model twice and do some weird merging of detections, but that can lead to double positives in some of the edge cases. So let's quickly just run it one last time in its original configuration. Off by 1 errors again. Okay, so the first solution proposed was actually using ImageOps, the very same ImageOps that are shown somewhere here. ImageOps preprocessing. There we go. .preprocess. So what I'll do is I'll copy the original Stardist code. Paste that here. One thing we do need to change is the path for where our model is located. I'll just copy this and paste it right here. Also, something I never understood is declaring variables in Groovy. Like, what's the difference between var def and simply not even pre-basing any of these things with a statement? Never really understood the reason why, but hey, it is what it is. So, we have our model. This is DSP 2018 heavy augment.pb. Right. So this is a model which has been trained on DAPI stained nuclei. The goal, what we're trying to achieve here is how can we trick Stardist into thinking it's receiving a DAPI image as an input. And that's where pre-processing comes into play. So one of the proposed solutions by Research Associate was to have a set of pre-processing steps that would basically perform the deconvolution, extract the hematoxylin 0 and brown 1, or DAB 1 stains, sum them together, and, well, apply a median filter optionally, divide all values by 2. I'm guessing to avoid any values exceeding the 255-bit depth of an 8-bit image. But we'll take it even one step simpler and go with the bare minimum for preprocessing steps. So as the name might suggest, preprocessing typically has to be run before the rest of the stuff gets built. And now we need to specify stains. So stains are, well, from the image data, getCurrentImageData.getColorDeconvolutionStains. All right, we have stains. We're extracting the first two. I will comment the, well, actually, we need the summing, but I'll comment the median filter out and comment out the division. Channels. We need to specify that. No, we do not. And finally, normalization. So normalization is a big, big deal because after you perform the deconvolution, you now have basically this floating point precision data that can range anywhere from negative infinity to positive infinity. In reality, it's not that large of a range, but closer to like -1 to 2 or 3. But we do have to normalize it to a similar range to that of what DSP 2018 heavy augment was trained on. I believe we should be good to run. I just want to make sure it is running only on the selected object. Yep. All right. Let's run it. Cannot find image data. Might have had to put. Where do I reference? That's it. I'll just put this up here. Okay. So it's working, sort of. I mean, if we compare it to the previous alternative, which is just using hematoxylin alone, and we take a look here, yeah, slightly more brown stain nuclei are being detected. Well, can we further improve this? First off, I'm going to try and uncomment these two commented outlines. Maybe they're there for a reason, and maybe they improve detection. Yeah, potentially. Uh, Actually, not potential, almost amazingly. This is what I get for not trusting Research Associates code. You can actually see that it does a substantially well job in terms of detecting objects or cells, or nuclei in this case, that have a near maxed out optical density. Let's take a look at some of the deconvoluted channels. So this is how hematoxylin looks. This is how DAB looks. Keep in mind, I'm using the ranges set from the previous image, so you can see that when I click auto, or rather, so it'll give you a nice little bit of understanding if you do have extensive saturation. Yeah. So in the original image, there's next to no hematoxylin being generated as part of the convolution. But as we all know, nuclei will have DNA, and DNA should bind to hematoxylin. This isn't an issue of tissue biology or staining mishaps, but simply a limitation of acquiring bright field images and attempting to extract a signal from a signal that was not initially acquired. What I mean by this is when you do fluorescent microscopy, you have a fluorophore at a specific emission wavelength, and you have filters to capture and filter light such that you're only allowing that specific emission wavelength, or rather a band of emission, to get absorbed by the microscope and consequently imaged. In bright field microscopy, you are capturing visible light, which is a fairly broad range, anywhere from 400 to 700 nanometers. And from this information, you're encoding it into a 3-channel image, which you are then attempting to deconvolute. Now, deconvolution is simply the process of attempting to extract one particular signal from a mix of signals. And this will have limitations, again, with high optical density cases. So these really intense dab stained nuclei are not going to be deconvoluted as well as other less saturated samples. In a nutshell, if you have intense dab staining, that's going to yield a lot of headaches and issues with regards to cell detection. Now, one of the reasons I don't recommend using dab staining is because the results of any analysis are going to be dependent on the quality of your deconvolution, as well as the parameters used, types of models used for deconvolution, and a wide variety of other confounding factors, which can hinder reproducibility in a new data set. In immunofluorescent microscopy, at least you don't have to deal with deconvolution, but there are some limiting factors with any imaging modality. Okay, so here we have code, and we've demonstrated that this code does a reasonably good job in terms of cell detection. Other ways we can improve this model is either by adjusting the extent of median filtering. I believe 2, for whatever reason, is the maximum, so not sure why. I don't believe division will have that big of a impact on model performance because we already perform normalization. If I'm not mistaken, it literally had no impact. Yeah, if you're dividing by constant or adding by a constant to all values in an image, when you're normalizing it, then it's not going to make any noticeable difference. So let's see if I've answered the question sufficiently. I mean, I did respond to this as well. Shows me code. Number of input channels should be a multiple of 3, but got 1. Yeah, so the reason being is that the output of all of this pre-processing will be a single channel image or single channel tile. If you're using a model that was trained on 3 images or 3 channels, like DSP, HE, or whatever the H&E trained model is, that requires a red, green, and blue channel, and that's what it's looking for cell detection. But in our case, we're only passing a single channel image that we're effectively trying to mimic as a DAPI stain section. So as a result, you'll need to use DSP 2018 Heavy Augment or any other channel trained on a single channel fluorescent image. So that should answer your question as to why the bright field model won't work. Different number of channels are being passed. You can't predict, you can't run model inference on a sample that has a different number of channels than what you trained your model on. And then yeah, Pete also has his own solution, but you can check the forums for that. Yeah, I mean, at this point, you can basically play around with some of the parameters like pixel size, threshold. If we lower the threshold, ultimately we're going to be picking up more entities. Whether or not those entities are actually true cells, well, that's up for discussion. You can perform filtering and deleting image objects below a certain size, as done in Universal Stardist for QuPath, but again, this is more for people, more for like I guess you could say a discussion for super users of QuPath. Because if you're at the stage where you're trying to basically modify a Stardist builder to support DAB-stained cell detection, that's not what I really call basic QuPath usage. Nonetheless, I hope this video was still informative to people of all QuPath experiences. If you have any questions, comments, or concerns, feel free to let me know. But other than that, I hope this serves as a reasonable framework for understanding how one could go about detecting nuclei with really intense DAB or hematoxylin staining using Stardist. Of course, the better solution would be to train a model by yourself, but even to this day, I haven't done it. And it requires a lot of time and effort and, well, computational resources. Anyways, yeah, if you have any questions, comments, or concerns, let me know, and yeah, I'll post this video on the forum for anyone else who, might find this interesting. All right.